Hello, I'm Sergey Bratus. I'm here to talk about work that is not mine. Because for the last 6 years, as you just heard, I was signing papers so that people could get funding for cool work. Of course, this starts with obligatory disclaimers. Take one. This is other people's work. I helped pose the problems. We're going to talk about how and why I did this. And what I hope to tell you, because they are all here potential DARPA performers. Some of you may be potential DARPA program managers. I'm going to tell you how this worked, and you'll judge for yourself what came out and whether this was worth it. Now, this is... thank you. This is a very personal and biased view of a great domain delivered by a former mathematician. And this does not represent the Department of Defense or any part of the United States government. With that, what is DARPA? I mean, you've all heard of DARPA of some DARPA project, the internet, the modern desktop, the first chess-playing program, the Lisp machine. They were all DARPA programs, and as they say, as a DARPA program manager, if you don't create an internet, you just get a B. And thank you for your service. But more recently, voice assistants, Siri, was known as PAL, or Professional Assistant That Learns, a DARPA project. Self-driving cars, which in the first self-driving challenge all failed miserably. It was just flipped over, if that. And then, of course, now we have self-driving vehicles because that initial investment de-risked it for industry. Quite the same thing happened with automatic reasoning about programs, symbolic executions, and things like that, with the Cyber Grand Challenge, where you had machines hacking machines on stage in Paris, in Vegas, at one of those DEF CONs. Well, that was then. Now, AI and cyber, large language models, hacking and defending programs and each other are running now, with the finals coming up in Vegas this year. So DARPA does all of those things, and the key point is that this is high risk, high reward. Peer review will not cut it. Basically, peer review will judge all of these things too risky. You keep hearing about peer review as something that our science establishment is founded on. Well, basically, DARPA steps in when that fails. What did I do there? I was looking at nothing so grand as an internet. I was looking at making software just a little bit more transparent and resilient and reliable. And I started with machine-readable, unambiguous format definitions that give you parsers that aren't pwned the moment a malformed input hits them. Then what I'm going to talk about today, which is closer to this audience, is rapid binary patching with assurance. Downloading gigabytes of recompiled software every other Tuesday is not great. This is not how you secure critical infrastructure. Of course, software is with us to stay. Unix is going to be 100-year software. It's already quite old. But it is everywhere, and legacy software is everywhere. How do you automatically refactor it and incrementally enhance it so that it doesn't fall apart? I started another program which basically looked to find and mitigate the parts of your target that the attackers find ever so convenient, the so-called weird machines or emergent execution behaviors, where you're really providing a general purpose programming engine to the attackers unwittingly by design. That is a problem with so many pieces of software. We've seen those exploits in the wild. And, of course, what else do you want? Well, you want to be able to have the transparency once you know that you have a vulnerability, how this vulnerability is reachable. Reachability is the hardest problem. Symbolic execution, backward slicing, and all of those other techniques get you only so far. What if your compilers, your linkers, would leave you a trail of breadcrumbs, and you might call it enhanced software bill of materials, but what I'm really thinking of is something like super dwarf, something that has not only symbols, but flows. Wouldn't that be nice? Well, of course, we're dreaming big. Our first generation of tools will probably crash and burn. And then maybe we'll get self-driving cars, self-healing software, that kind of thing. So, for some longer perspective, if a 1960s programmer looked at our software today, they would pretty much recognize everything, right? High-level languages, compilers, linkers, libraries, all of that was already there, and Admiral Grace Hopper is looking at you approvingly, or perhaps disapprovingly, but also we get this really hard problem that once you produce the binary, it's completely opaque, unmaintainable, not sustainable in any way, shape, or form. You can just replace it. If we build houses like this, then we would tear down a house literally to remodel a room. This is what our software maintenance looks like. And, you know, there is some theory to that. You patch a thing, and of course then you must rebuild it. Which means that you had better have your original build process with exactly the same version of the compiler that you had, and all the other tooling, and that exact SDK that you used back then in the embedded space, because if not, chances are your original, well-tested and deployed binary was correct by grace of so many lucky coincidences in the compiler. Unintended behaviors, undefined behaviors, just looking up just exactly right. So, rebuilding patched source is in itself a problem. What if you don't have the source? Or what if you have the source, but not all of it? What if you don't have the SDK? What if that 486 machine on which your hardware security token still works is, well, not well? You can decompile, right? Yay, verily. You can decompile. Decompiled code is absolutely worthless for anything but reading, right? So, you can't recompile it. You have absolutely no guarantees that it looks anything like the original code. You absolutely have no guarantees. It was a great achievement, the idea of decompilation, and Cristina Cifuentes' structuring of this as a graph, mathematical graph problem. But, yeah. So what if you could make use of any artifacts that you can, in fact, that you might, in fact, have, decompilation, or snippets of original source code, or maybe source code that you think is close to what the original source code was. And then you, instead of producing this one shot, give me your best guess, you slowly bent it towards aligning with your existing binary, so that when you have a trivial bug to patch, a buffer overflow or some such, you know exactly where in the binary code fabric it is, and you can compile your one-line fix and distribute it over the binary wherever it needs to go, with assurance that you understand all the changes that you're introducing to the execution paths. So you want decompilers that are really lifters and aligners. And you don't want a compiler, you want a recompiler. You want something that is aware of your hard-won working binary and preserves as much of it as it can with the analysis where it can. And if you're a DARPA program manager, you say, okay, these are the two technical areas. We want better goal-driven decompilers. We're going to change decompilation. And then we want this new kind of a thing of a recompiler that guarantees non-interference with the baseline and accounts for every change and gives you some certificate, some proof that you understand all the changes. And then you can go patch satellites. Today, NASA has this interesting problem. They also use compilers. When they need to patch a satellite in space, or in fact on the ground a year before launch, this is how rigorously they test. They basically consider it done and launched. They need to go through this tortuous loop of test, modify, recompile, rebuild, and it's as hard for them as it is for everyone else, or maybe harder. And of course, when your satellite passes overhead, you don't get all that many passes to upload your fix. So you had better have a micro patch, and you'd better have it assured, because if you don't hit it just right, you have a dead asset, a dead bird in space. Too sad. So what we're looking at in this scenario of space micropatching is hitting the binary with every tool you've got: decompilation, type inference, alignment with existing code. Then going through candidate patches that express your idea of a fix in the way engineer thinks about it. Here's a line of C, or here's a line of equation. And then, of course, program analysis is not magic. Most of the time, you can't assure or reason about any particular program. Halting problem, Rice's theorem, any non-trivial problem here is hard. But you can choose the patch. When you're in the control of the patch, then perhaps you can solve it. If not for this one, then for the next candidate. And then here's how DARPA works. It decomposes the problem, and then it creates a hard forcing function for performers who submit their proposals to this program formulation. And as a proposer, you say, I am proposing this kind of a new decompilation technique that allows me to use any available artifacts, including what I think is the code that might align with what's in there in the firmware. Or I'm going to do this recompiler or this new binary analysis that ensures that all the traces through this binary after this recompilation are exactly the same or semantically equivalent. But then you have to validate those assumptions. And this is the evaluation. So you get a forcing function of challenges. Do it on a commodity embedded system first, kind of like a telematics unit. Then do it on something that matters, like an engine controller. Here you see an engine controller for a 15-liter engine, also used on 6.7-liter engines. And then on a system, a heavy vehicle. It's out there on the roads. It has a bus that's kind of like CAN bus. It's called J1939. And you really, really want these things to be secure, despite people being able to call in through the telematics units that the Department of Transportation mandated on all such fleet. This is lovely. Suddenly your ECU can be attacked from your modem. And now you need to patch your ECU. And we're going to check. So here's an engine standing in a lab with a dynamometer and the exhaust manifold that validates that you have indeed patched your critical software that is running your engine. And of course, this is a computer behind all of this thermal shielding and funny buses. So now, people patch binaries all the time. This is a boutique exercise. You all do this. Can you scale this up. No. That sort of an idea that you can fix a large fleet of somewhat diverse embedded systems by just hiring boutique reverse engineering companies. No, that doesn't scale. So people have always tried to introduce some kind of automation and mathematics into this. Hallerflake, Thomas Dalian, in 2006 wanted a set of mathematical challenges for reverse engineering. And in fact, we've been making good progress on these. This is an awesome talk, and it aged very well. And now you recognize that all of these questions, how do you decompose a binary module? How do you combine multiple reasoning algorithms and make them talk together? How you represent this software? All of these are essentially mathematical problems, computer science problems, algorithmic problems. So, the performers, with the task of patching a real heavy vehicle, created some tools. And these tools are all on GitHub, and I encourage you to look at them. I will say a few words about each tool and what it did, but here is one thing that, to me, stood out over all of those attempts to get the engineers who understand the problem, or the developers who understand the problem, but cannot extract firmware, cannot automatically unpack firmware, cannot analyze binaries, are not PhDs in formal verification. What even is formal verification, right? My definition of formal methods is, it's that which continually surprises domain experts. It just continually reveals corner cases that they missed. If it's not it, then it's not very valuable. So this theme that came out of this is that all those tools lift to some kind of an intermediate representation. And we see IRs everywhere, and they're all disjoint, and they're all ad hoc. Be it MLIR, P-code, VEX, binary engine has 7, 3 public. Well, what we really need is a set of IRs that works together across different levels and captures the level at which you want the fix. Because this is the level to reason about the fix. And Trail of Bits created this set of IRs called VAST. And these are dialects of MLIR. And they were informed by all the other previous work that I mentioned. And we even achieved a partial interoperation. But bugs span the semantic gaps. So should analysis. So should IRs. And what you have there is this leaning tower reaching for higher concepts that allows you to do your analysis or do your patching or do your ad hoc recompilation or your flow analysis, if you will, up and down that stack. That way, you are not losing binary fidelity, and you are working at a comfortable level for your patch provider that can be related to source code or what have you, even your MATLAB, if you will. In fact, it could be a tree of IRs that are baked to order. And it may well be that LLMs might help with that and at the same time cure their own hallucinations. Because if you have an intermediate representation that has strictly defined semantics, you can tell what is a hallucination and what is not. You can just validate this. But I'm going to have a panel on this at Recon, assembling all these people who have been doing those things. And, well, if you make it, Hopefully you'll be entertained. But I do really think that this is the future, that those kinds of multi-level, interrelated, interoperable IRs are going to carry forward our software sustainment. Okay, so what did we make with all of this grand vision? Well, I think many of you know OFRAK. This is a modular framework for dealing with anything binary image, anything firmware, built by Red Balloon. I understand they presented it last year. Well, this was an outcome of this challenge in assured micropatching. And it made things well-defined for the people who were not reversers. In fact, we had automotive engineers using this framework and assuring themselves that their all-important patch to their engine actually works, is not going to stall, is not going to kill people. Nobody is going to go to jail. Basically, we're talking about people who need to convince themselves that they are not going to jail if something goes sideways. And you will notice that it is compatible with IDA, Binja, and Ghidra, because this is what we should be doing. And it has a wonderful old-timey interface. It just warms my heart, seeing binary and colors. They told me that it saved them 2 orders of magnitude on various tasks that they did in their main line of business. We did measure a 16-time speed up in creating a patch and assuring a patch. And somewhere in that tool, in the early version of the tool, was an ASCII picture of me, I guess. But you see, they were tested on things like, here's this board, it has the code we don't want. We really want to get rid of that code because we don't want that in our environment. How can we make it sure that it's dead, that we understand all of it and the device doesn't break? Not quite a micro patch, but also a useful exercise in a controlled environment. So, starting small, we want to get back at what are all these object files and little C source units of compilation that went into an image. So JHU-APL developed a better version of their code cut tool. You may have encountered this in the original version. It segmented your modules by looking at where the backwards jump went. You don't have forward jumps across modules, hopefully. But they did this with some neural learning, and in the end, they were able to decompose a rather large and messy graphs into modular graphs. We're talking architecture recovery. People call it SBOM. I call it enhanced SBOM if you give me flows between those modules. But they were quite successful. You can download that tool and play with it. Very often, you do have some code, NASA certainly does, just not ways to precisely rebuild it. So you want to align it against the binary. And we had Binary Ninja take on this task of finding the most likely code alignment using techniques that harken back to the history of decompilation, graph matching, graph analysis. They had a lot of training. Well, all of GitHub is out there. So if you're using one of their tools, you can ask for this feature. It aligns source code to target binary, and it does a very good job. It finds standard libraries like OpenSSL, which have all of those lovely bugs that have been embedded in that SDK since times immemorial. And it runs at pretty much your speed of typing, which is quite amazing. Graph algorithms are very, very nice. I mean, we knew that. BinDiff was a graph algorithm matcher. But speaking of Thomas Dalian and his contributions. All right. So supposing you have a patch candidate, how do you convince yourself that you understand every aspect, every change to the basic blocks and flows that it introduces? Well, you have to run a lot of binary analysis. This is local binary analysis. You start small. You presume that the change is small. Security fixes usually are, unless you have to throw out a cryptographic algorithm and replace it with another one, which is a whole different kettle of fish, which we handled in the vSpells program. But that's a story for another time. So what you end up with is a multicolored set of basic blocks. Think of it like Ghidra or IDA, except what you get is code paths. And you get the conditions under which the blocks behave differently. And you can, as it turns out, you can wade your way to a proof if your solvers are fast enough. And you can have a very long formula, which is a certificate of this verification. And it models a lot of things: stack, heap, memory, all those others. Now, of course, what you want to do is patch your binaries in something that's pseudocode, not even C. I mean, who cares? You want to patch things in eBPF, a domain-specific language that knows what your structs are and how they are represented. And MIT and Arno Labs did this thing that they call the multifocal relational analysis, picking the right representation and operating on what looks like C code, producing a proof. And again, since the point is to convince yourself that you understand every change to every code path that you introduced with this, you are shown those divergent code paths, and you're ultimately being the judge. Now, verification is an extremely hard problem. You listen to academics who talk about verified computing, program verification. You start with a specification, you generate everything from the specification, then you prove that it is correct at all levels, and you have full functional correctness down to your RISC-V, blue spec, or some formal expression of what your processor does. And of course, this is not how people create systems. This is not how people run software. People run software, people test units until they think they work. Then they put them together. This magical moment is called integration. They find out that the whole doesn't work at all. Then there is a frenetic several months until they are sort of hammered into shape, and it does work. And in the end, you have a working binary that's worth all the person hours that you've spent testing it. Change something, change very little, and you can no longer assure that all of your tests will pass. So you need to be able to break the non-transparency, the opaqueness of the binary, and reason about the small changes. And this is what we did. Now, we had several other systems called, one was called Patcher X, developed by Purdue and EPFL. And it modeled hardware abstraction layer. You see hallucinator down in that stack. And it was used to validate the patch to ArduPilot that changed some of the control laws. And it did a variety of static and semantic analysis. And again, it's there. Now, what if there is no compiler whatsoever? The compiler is dead and buried. It turns out that compilation is kind of like constraint solving. And you can, in fact, there was an academic work called Unison, a compiler that acted by taking the specification of what you wanted and solving the constraint problem with a description of instruction set architecture that produced a compilation. So how many instructions, you ask? About 100. So if you train one of those systems to produce a binary code in the style of your target, and you have the target, you can learn, you can, in fact, run this sort of a tightening, ratcheting loop. It's called CGIS, counterexample guided analysis. This is what Microsoft has been using to validate their drivers, which arguably accounts for fewer screens of death. In USB, in particular, I'm looking at this cable that I just stuck in. Great. Hopefully Apple does the same. Formal verification, yay. But it turns out that, in fact, you can emulate a compiler by treating compilation as a constraint solving exercise. And this tool from Draper Labs is also online. And so we come to this. The process for sustaining software is today still in industry usage. Tear down the house and rebuild it anew every time you need to make a change, which is completely unsustainable. And with the mass of code deployed in vehicles, critical infrastructure, medical devices, what have you, that's just a non-starter. So we should be doing some things to the legacy software to break that opacity of binaries and inability to reason about small changes in them. And going forward, we must, whatever we do, whenever we are in the compilation, in the building cycle, we must produce metadata that helps us reason about compiled code, transform compiled code, post-compilation. That's what will account for actual maintenance. And we might call it an enhanced SBOM if you are into executive orders that prescribe that thou shalt produce an SBOM for any piece of software that at least the government will buy off of you. We need new kinds of tools. We need tools that are much smarter than cross module linkers and optimizing linkers. We need tools that are patchers that load a patch the way you load a library. I mean, why does that work when it does? Well, there is a structure there that allows the dynamic linker loader to safely, quote unquote, load a change in a prescribed place. Who does this on the scale of every machine in the data center? eBPF. Netflix and Facebook are reported to use up to 12 eBPF snippets, changing the production kernel in their production servers in their data centers, and those data centers do not burn. What would happen if you were to write C lines of C code that modified the kernel per production server with your interns? Boom. So this works, but that needs to stop being a cute hack or a multi-million-dollar hack with multiple Google FTEs and others working in it, and start being an actual well-described, semantically well-defined way of recomposing software, transforming software post-compilation. And with this, I leave you. And these threads that were developed in prior DARPA programs, my programs, ongoing programs, are all coming together. And if you can make this resilient software systems colloquium in June. I think registration closes tomorrow. So you still can. And hopefully we can really change the way we make software. Thank you for your time.
All right. Thank you very much for your talk. We have time for questions. I guess I can start. So I would assume that if you have a big static binary, then binary patching is probably a pretty hard problem. Even if it's a one-line C change, it could be great effect on the compiled binary. But as you already mentioned, you have the dynamic libraries which can be linked in. So what if instead of compiling this one huge blob, we would just modularize the binary more and more? So every module is tiny, so we can just replace the whole module in a dynamic linker fashion. Wouldn't that already mostly solve the problem?
Yes and no. Right? So first, let's take one large binary, right? So you need to decompose it. You need to understand what units were put together by the linker. What are their interfaces? Because unless you do this, you will not be able to reason about code paths, right? You will have enormous state explosion. On the other hand, many of those analyses are local. So once you split up and splay out a big binary, you can in fact have a reasonably scaling argument, as it turns out. I mean, we didn't blow up our engine, and we didn't blow up other simulated environments, like a simulated satellite. But then, of course, you coming to your, can we make this really small? Well, small is not quite the sufficient condition. The really sufficient condition is composable. So well described that you know all of the flows between those small units. If these are an uncontrollable mess, if the data that travels between those units is not well defined, then you don't really have reasoning capability and safety. But think of dwarf. Dwarf, the debugging format and exception handling format, let's not forget it. So any C++ program carries with it a virtual machine that knows exactly where your variables are, exactly where your stack is, what they're called, and can mess with it very, very effectively, right? Unwinding frames is the least of the things that it can do. We had quite a bit of fun with exploiting dwarf 10 years ago. But imagine dwarf that also knows not just where things are, but how they talk to each other, what the data flows are. That way, you might be able to track back from your crash, not within, maybe a few lines of code or not within a single module, but possibly across modules. So yes, metadata should do this. Smart metadata should do this smartly.
All right, thank you. Question over. Yeah.
How does you're talking about this super dwarf that gives you more insight. How does this work with binaries that are purposely stripped of that metadata for whatever reason?
Well, it doesn't, right? So you need to recover, you need to do type inference, right? So dwarf is a funny thing. Linked somewhere in my slides, which I think are going to be posted, is a link to a blog post about what dwarf really does. And it is very precise as to where things are when it's about exception handling. When it's about debugging, it's best effort. So it will lie to you. And even if you have that, you need to do type inference. But binary type inference has made great progress. And this is, again, one of those things where somebody discovers the right piece of math and things go just so much better. You know what this is wrapped up in? The right choice of IRs. So Grammatech had this system called retyped, which since then has been re-implemented in Anger. And it's just one of those things when you can recover quite a lot of typing just by looking at the binary. Rolf Rolles had a wonderful talk about recovering C++ types. And this is, of course, also what Thomas Dahlin asked for back then in 2006. So inference, suddenly type inference becomes much less of an academic exercise and much more of, here, I can recover. And then you have an architecture that will allow you to patch your binary faithfully with just a few bytes, like in that anecdote, hit the engine with a hammer. That'll be $100. What for? Well, here's the split. $1 for the actual hit, 99 for knowing where. And you just need that data that is the know where. That's the promise of those IRs and metadata.
Thank you very much. Wonderful talk and wonderful overview, Sergey. Source code is an IP. Well, at least we treat that as an IP, at least in some context. The opaqueness of a binary has been perceived for a long time as a way of protecting that IP. Carrying that information that we need from source to binary to actually reconstruct in a meaningful and semantical way, that means basically giving away the source code from the binary. Well, for many of the reverse engineering in the world, this is not really a big problem. We get to semantically equivalent, let's say, decompilation, which basically give away still the idea. I wonder how this would be received in reality by society when there is value attached to source code and binary seems to be your protection.
Mm-hmm. So, wouldn't it be nice if we lived in a completely free software world, right? But of course, every proprietary bit of software is something like 70 to 80% free software, according to some people taking that census. But more to the point, I did have this conversation with people who were concerned with anti-tempering. And to them, my response was, we're talking about being able to transform post-compilation code arbitrarily with full knowledge of what it does. So you can keep this knowledge. The kind of obfuscatory transformations that you can apply with that semantic metadata are so much stronger than anything else you can do. Because when you do an ad hoc obfuscator, you're basically in the position of trying things out and seeing if they break your product. And that's not great. So you have to be reserved. You have to be cautious. One of the really interesting aspects of formal methods, that is to say, mechanized definitions of what you want that are reasoned about mechanically in faithfulness to the code enforced by automatic tool, is that it makes engineers a lot bolder to try new things. Because when things break, you will know where. You could apply the same thing to your anti-temper and your obfuscation if you so want. I mean, you can have cryptographic strength in those transformations rather than opaqueness, if you want that.
All right, we're almost out of time. Let's do one last question.
I wanted to get your opinion on it. It seems like, the core problem here to the previous question is that this is really the inherent problem here is one that we have, massive amounts of the current software stack that are, opaque and under censorship regimes. But if we, pivot our view to more FOSS building methods, that this really isn't a problem that we need to deal with in the future. And so I guess my question is, given more modern build systems like Geeks, which posit let's have a declarative build process in which we go from literally the smallest part of the build process up until reproducible binaries. Just, it seems to me like that's the path forward for much of this work, rather than just saying, geez, I'm having such a tantrum dealing with all these closed source binaries and people who don't build in FOSS.
Yeah, that's exactly right. I mean, the solution here is the ability to reason about code. Some people call it cyber reasoning. Some people call it resilience reasoning. But the solution is mechanized reasoning. So putting together the right kind of data to support that reasoning mathematically and making it palatable algorithmically, it may cost you, but debugging a bug that is not reproducible and only shows once in a full moon in your cloud data center at the scale of that data center, that's actually worse. So this is why AWS, for example, has a large formal methods group. And they recently wrote a number of blog posts about how using these methods saved them from bugs that were there for years and were not understood and root caused for years. And then they were eliminated by essentially mechanizing that kind of reasoning. Now, you can support this with this additional metadata. You can protect it based on that additional metadata if you so want. But I would say that, it's sort of a reflection on the sad situation of things. I mean, replicability is table stakes, right? The fact that you can rebuild something exactly the way it was just by hitting the button again tells you very little about what effects a small change will have. And that's the next thing, right? Replicability in science is table stakes. Well, the next thing in physical sciences is understanding the effects of small changes. This is why calculus is so central to things, to life on Earth. Do we have that for software? No, we still don't. I mean, we might be inching up on that. But, yeah, I mean, to your point, this is exactly thus. Just saying that software sucks will not fix software.
Thank you.
Math might.
I know there's more questions in the crowd, but unfortunately we run out of time. I'm sure you can find Sergey later and ask him. Please give another applause for Sergey.
And thank you for your patience. All the credit goes to the people who actually did the work. Don't forget.